See, abnormal molar masses are due to two reasons. Mainly, the first one is molecular association. The second one is molecular dissociation. Okay. Now let us see what molecular association is and how to find degree of association. Okay. See, in general, because of the molecular association, number of particles decreases. See, when number of particles decreases, it actually leads to decrease in the magnitude of colligative property, because these two are directly related. Okay. Now, when magnitude of colligative property decreases, molar mass of the solute increases, because see, these two are directly proportional, whereas these two are inversely proportional. So when number of particles increases, the magnitude of colligative property also, when number of particles decreases, the magnitude of colligative property also decreases, but at the same time, molar mass of the solute increases. Let us again take the same old example of acetic acid in benzene. See, when acetic acid is dissolved in benzene, two molecules of acetic acid unite to form a dimer. Dimeric form of acetic acid is formed. In this case, if suppose we assume 100% association, we can say that the number of particles is halved, isn't it? 2 is becoming 1. Two molecules are combining to form one dimer. So number of particles is halved. As a result, magnitude of colligative property is also halved. Therefore, molar mass is doubled. Okay. See, this molar mass, of course, can be given as normal molar mass is, of course, 60, but the observed one from one of the colligative properties is going to be 120. This is what we considered as abnormal molar mass. has to be 60, but is observed to be 120. Okay, so this is all because of association. Like I said earlier also, every time it may not be the 100% association of the molecules. It may be something different, something less than that. So, what percent of the molecules have undergone association? Let us see now. Now, it's a calculation of degree of association. First of all, what is degree of association? See, it can be given as number of molecules associated out of the total number of molecules that we have started with. Okay. Of course, you can also consider moles instead of molecules. This is your alpha. Molecules or moles. Okay. Now, let us derive an expression for alpha. Look at this. See, n molecules, or you can say n moles, giving rise to just one mole. Okay. Now let us see. Before association, let this be one. I mean, let us suppose that we have started with 1 mole of A. Of course, 1 molecule of A doesn't make any difference. Degree of association, let this be alpha. See, for n, if it is 1, for alpha it would be alpha into 1 by n, isn't it? So let me write this as alpha by n, alpha into 1 by n, right? When n is giving rise to 1, alpha gives rise to alpha by n. So after dissociation, sorry, after association, if you observe, it will be 1 minus alpha in case of the reactant and alpha by n in case of the product, right? Now we know that 1/2 factor I is the number of particles after association or dissociation by before association or dissociation. So after, okay, let me write this. After association, let us take only association by before association, right? Now this can be written as, come on, 1 minus alpha plus alpha by n by, of course, 1. Now this can be written as, see, this is 1 minus alpha is taken as common, 1 minus 1 by n, that is equal to I. Now therefore I can be written as, of course, it is 1 minus alpha into 1 minus 1 by n. That's what we got. Now this can be written as alpha is equal to 1 minus I by 1 minus 1 by n. This is a very important relation. N is the number of molecules or number of moles that you have started with. Okay. Now we know that I is equal to M normal by M observed, right? Substituting this, we get 1 minus M normal by M observed by 1 minus 1 by n. Or finally, it can be written as M observed minus M normal by M observed into N by N minus 1, right? So this is the final expression for alpha. Okay. So these two are very important. Now let us go for the calculation of degree of dissociation. Okay. Now, see, first of all, degree of dissociation. In fact, leads to increase in the number of particles, right? See, when number of particles increases, magnitude of the colligative property also increases. When magnitude of the colligative property increases, molar mass of the solute decreases. The first two are directly related. The last two are inversely related. So increases, increases. But this one decreases. Let us take an example. See, when sodium chloride is dissolved in water, it ionizes to form Na plus and Cl minus. Assuming 100% dissociation, we can say that the number of particles is doubled. When number of particles is doubled, the magnitude of colligative property is also doubled. And finally, the molar mass of solute is halved. So, the normal molar mass of sodium chloride is 58.5, whereas the observed one from one of the colligative properties will be 29.25. No problem. AMU. So it's exactly halved because we have assumed 100% dissociation. But see, every time it may not be this 100%, right? Then what is the percentage of the reactant that has undergone dissociation? That can be calculated. Consider this reaction wherein one is giving rise to many. Earlier it was n giving rise to 1. I mean many giving rise to 1 in case of association. But here it is 1 giving rise to many. Come on. See, before dissociation, let us suppose we have started with 1. Coming to degree of dissociation, alpha. Now, see, when 1 is giving rise to n, alpha gives rise to how much? Nothing but alpha into n by 1, right? So let me write this as n alpha. Okay. Now, after dissociation, it will be 1 minus alpha, right? Started with 1, alpha is what it has dissociated. So we are left out with 1 minus alpha. Now again, I can be given as number of particles after dissociation by before dissociation, right? Now, what is the number of particles after dissociation? 1 minus alpha plus n alpha by we have actually started with just one particle. As usual, it's 1. Come on, let us take alpha as common. Let me give it as 1 plus alpha into n minus 1. Okay. So I is equal to 1 plus alpha into n minus 1. Now alpha can be written as I minus 1 by n minus 1. Okay. So this is an important relation. In case of association, it was 1 minus, because the number of particles is anyway less than 1. 1 minus I by 1 minus 1 by n it was. In this case, it is I minus 1 by n minus 1. Now, we know that I is equal to m normal by m observed, right? So substituting that in alpha expression, I minus 1 by n minus 1. So this is m normal minus m observed by m observed into 1 minus into 1 by n minus 1. So this is again very important. Okay. These are the expressions for degree of dissociation, degree of association.